This is lesson 6.3, factoring special products. Our learning objectives are to factor perfect square trinomials, factor difference of squares, and factor sum and difference of cubes. Okay, so one thing that's important for you as an algebra student is to know your perfect squares from 1 to 16 and your perfect cubes from 1 to 10. Now, some students say, oh, you want me to memorize that? And I say, no, I want you to know it. I want you to have it in your heart and understand that 1 squared is 1, and 2 squared is 4, and 3 squared is 9, and 4 squared is 16, and 5 squared is 25, and 6 squared is 36, and 7 squared is 49, and 8 squared is 64. Not only that, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, 15 squared is 225, and 16 squared is 256. I want you to know in your hearts that 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, 8 cubed is 512, 9 cubed is 729, and 10 cubed is 1000. So these things, as they come up, these numbers, are going to be critical to your success as we move forward. And if you can recognize them quickly, then you will succeed. If you don't recognize them, then you will struggle. So take the time to get used to these numbers. In fact, we're going to do it a different way than you're used to. When you see a problem that says 196, your brain will go backwards and say that's 14 squared. So it's going to turn this number, 196, into 14 squared. Usually your brain has worked the other way, right? When you see 5 squared, you turn it into 25. But no, this is now what we're going to do. We're going to take 25 when we see it, and we're going to turn it into 5 squared. We're going to go kind of backwards from what you're used to thinking of these perfect squares and perfect cubes as. All right. So yeah, you see a number like 343, you turn it into 7 cubed, and then you can proceed. All right. And it'll make sense as we continue forward in this lesson why we're going to have to do that. So take a moment, pause the video, get very comfortable with all of these perfect square numbers that you see, and let's proceed. So our first objective today is to factor perfect square trinomials. And a perfect square trinomial pattern, it looks like this. This is a perfect square trinomial, okay? A squared plus 2 times A times B plus B squared. And we can factor it into A plus B squared. Whatever A and B are, we can take them and we can factor into this. Now, if I see A squared minus 2 times A times B plus B squared, I can turn it into A minus B squared. We talked about these perfect square trinomial patterns in a previous lesson. But we were talking about how to expand it, how to multiply it, right? If I see A plus B squared, squaring something is multiplying that thing by itself. So I take A plus B and multiply it by A plus B. And when we FOIL it, we get this. Or likewise, A minus B squared is A minus B times A minus B. When we FOIL it, we get this. Great. Now we're going to work backwards. We're going to go from the trinomial to the perfect square binomial, right? Now, how do you factor perfect square trinomials? Here's a quick three-step process. Step one, ask, does the trinomial fit the pattern, either this or this? Okay, and to check that, are the first and last terms perfect squares? Write them as squares, right? So that's why we have to know our perfect squares really well, because we have to recognize those perfect squares as they come up. Looking at this first example where I have 9x squared plus 12x plus 4, I notice the first value is 9, which is a perfect square. 9 is 3 squared. And then 4, well, 4 is a perfect square of 2 squared, right? This one, 81 and 16. My brain has to recognize, well, 81, that is 9 squared, right? 81 is 9 squared. 16, that's 4 squared, right? So we're going backwards. When we see these numbers, 9, 4, 81, 16, we have to recognize them as perfect squares and rewrite them, okay? Now, the second part is check the middle term. Is it 2 times A times B? So like this example, if I have 12x, is it going to be 3 times 2 times 2? Yes, that is 3 times 2 times 2. We'll address that a little more in depth as we move forward. But if it satisfies these two conditions, then it is a perfect square trinomial. And so we proceed to step 2, and we can write the square of the binomial. Okay, so we can write it like this for this pattern, or like this if it was like this pattern. And then we could always check to make sure that we have factored correctly by multiplying it out. So let's go ahead and jump into this. And we're going to factor we're going to factor 4 trinomials using the perfect square trinomial factoring method. So here I go. I see 9x squared plus 12x plus 4. And I immediately can turn 9x into 3x squared. Okay, there's 9x squared. I can write as 3x squared. Why can I do that? Because 3 squared is 9 and x squared is x squared. Okay? So you have to figure out what the value is right here that when you square it makes 9x squared. Now, looking at the last part over here, well, 4 is, I can write it as 2 squared. And then this 12x, can I multiply 2 times the a value, which is 3x, times the b value, which is 2, and get 12x? Well, yes, I can. 2 times 3x is 6x, and 6x times 2 is 12x. So this is a perfect square trinomial. Now that I've recognized it as a perfect square trinomial, the factoring is really fast. What I do is take the a value, 3x, and the b value, 2, and I put them in a binomial. And since this was a plus sign here, I put a plus there, right? So if this sign is positive, there's a plus that goes in here. So what have I done? I've taken this value here, wrote it there, this value here, wrote it there. And then lastly, I square the binomial. I'm multiplying that binomial by itself. Okay, so 3x plus 2 squared is the factored version of 9x squared plus 12x plus 4. Let's do this again so you start to get more comfortable. When I see 81y squared, my brain says, well, that's 9y squared. And when I see 16, my brain says, well, that's 4 squared. Okay, now I look at the middle term here, and I have to check to see if that fits this pattern, right? This is the a squared minus 2 times a times b plus b squared pattern, right? I'm thinking about this pattern. Why? Because of the minus sign that I see here and here. Okay, and so I say, well, is 2 times a, which is 9y, times 4 equal to negative 72y? Well, 2 times 9y is 18y, and 18y times 4 is 72y. So I'm good there. Okay, so this fits the pattern. And since it fits the pattern, I can write a binomial. And I put 9y, and I put 4 inside, and I put a minus sign, and I square it. Now, why did I do all of that stuff? Well, I took that 9y that's up there, and that 4, and I placed them in the binomial. And then I saw this minus sign, so I put that minus sign there, and then I squared that binomial. It's the binomial multiplied by itself. Okay, so there we go. We have factored this perfect square trinomial and got our answer. All right, well, let's try another. I see 36x squared plus 84xy plus 49y squared. And so when I look at this, I look at the first term and the last term. And 36 is 6 squared. So I could write 36x squared as 6x and then take that and square it. And then 49y squared, I could write that as, well, 49 is the square of 7. and I have y, and I square that, right? So 36x squared is 6x squared, and 49y squared is 7y squared. Because if I square, 6, right, 6 squared is 36, and x squared is x squared. And 7 squared is 49, and y squared is y squared. So that's why this is true. Now, let's check the middle term and say, well, is that 2 times a times b? In this case, 2 times 6x times 7y. And 2 times 6x is 12x, and 12x times 7y is 84xy. Yes, this is true. It checks out. So let's go ahead and factor this perfect square trinomial. We've just discovered it is a perfect square trinomial, so I write a binomial, and in the binomial, I place 6x and 7y, and I put addition between them, and I square it, and I'm done. And why have I done these things? Well, because I took the 6x and I put it there, and the 7y and I put it there, and I saw a plus sign here, so I put a plus sign there, and this is a binomial that is squared. I'm done. Great. Let's try one more as a practice. And when I see 100x squared y minus 80xy plus 16y, my brain says, wait, I see a GCF. I see a greatest common factor. And the greatest common factor that I see is a 4 and a y. So you are practicing seeing greatest common factors, but what is the GCF of all three of these terms? My brain analyzes and tells me it's 4y. You may want to create a list of all the prime factorizations of all three terms and circle the factors they have in common and combine them together to make the GCF, like we have practiced in section 6.1. So if you want extra practice on finding greatest common factors, refer back to section 6.1 lesson. Now, I have factored out a 4y, and so now what's remaining in the trinomial? So if I factor a 4y out of 100x squared y, right, 100 divided by 4 is 25. And then y divided by y cancels, and you still have the x squared left. Okay, so we have a 25x squared. Moving on, if I divide a 4y out of negative 80xy, well, that would leave me 80 divided by 4, which is 20, and y cancels, so I just have an x. There I have the result. And now if I take the third term, 16y, positive 16y, I divide it by 4y, then I'm left with, well, 16 divided by 4 is 4, and y divided by y is no y's. So I'm left with this. And you'll say, am I done factoring? And the answer is, well, no, because inside it looks like we have a perfect square trinomial. Let's confirm. I see a perfect square, 25 is 5 squared. And I see a perfect square on the end. It's 2 squared, right? 4 is 2 squared. And so let's see, is this truly a perfect square trinomial? Well, I'll rewrite 25x squared as 5x squared. And I'll rewrite 4 as 2 squared. Okay, so there we go. So those are like my A and B values of the factoring pattern. And now I'm going to check that middle term and say, well, is it 2 times A times B? Is that what it is? And 2 times 5x is 10x, and 10x times 2 is 20x. Yes, yes it is. Okay, so this is a perfect square trinomial. And so let's factor it. Now don't forget about that 4y GCF that you factored out at the beginning. And now let's write a 5x and a 2, and we're going to put a minus between it, and we're going to square that binomial. And we have now factored completely. And let me show you why I did what I did. Because, well, this 5x goes there, and this 2 goes there. And why did I put a minus? Well, because of that minus that was in that starting position. Okay, so we have now factored this perfect square trinomial. There you go, and you have seen my reasonings for why I have done what I've done, and this is the factored version here. Great. So go ahead and try some of these examples on the right-hand side, comparable to what we've just practiced. Let's move forward, and we're going to practice now factoring the difference of squares. So the difference of squares is another factoring pattern that you have to recognize as you move forward in algebra. Okay, so what is the difference of squares? Little reminder, the difference of squares pattern. If a and b are real numbers, then a squared minus b squared, when you factor it, equals a plus b times a minus b. Okay, so why do we call this the difference of squares pattern? Well, difference in math is subtraction. And two things that are being squared, right? A and b are being squared. So this is literally the difference of two things that are squared. When you factor those two things, when you recognize the difference of squares, and it will come up very often in the remainder of this course and in math courses beyond this, then you are going to take the base a and the base b and write them in two binomials, right? A and b and a and b, and then separate those two terms with a plus sign and a minus sign. So we put opposite signs in the two binomials, right? You could put the minus first and the plus second, or the plus first and the minus second. It will not matter because multiplication is commutative, meaning multiplication, it doesn't matter what order you decide to multiply in. Great. So let's get you used to some examples using the difference of squares pattern. And here is how you can factor the difference of squares in this four-step process. Step one, does the binomial fit the pattern? Right? Is it really the difference of two things that are squared? You have to ask yourself, so is this a difference instead of a sum, right? And are the first and last terms perfect squares? Well, it's a good thing you know your perfect squares up to 16 squared, because they're going to come in handy here. Now, step two, write them as squares, like write them as a squared and b squared. And then step three, factor as the product of conjugates. Now, conjugates are when you have the same two terms, a and b, in two binomials, but they have opposite signs. So a minus b is the conjugate of a plus b, and vice versa. A plus b is the conjugate of a minus b, however you want to think of it. Okay, these are two conjugates being multiplied together. And step four, check by multiplying. Okay, so let's jump into this. Let's look at example 6.27 through 6.30. Now, when I see 64y squared minus 1, my brain immediately says, well, this is 8y squared, right? Because 8 squared is 64 and y squared is y squared. And then I have a minus sign, and when I see 1, my brain tells me, hey, that is 1 squared. Okay, 1 is a perfect square. It's 1 squared. And so now that I've rewritten this, I can see the difference of two things that are squared very clearly. And so I quickly write two binomial sets of parentheses, and I put 8y at the start of each one, and I put 1 at the end of each one, and I separate them with a plus and minus sign. You see, these are conjugates of each other. 8y plus 1 times 8y minus 1. Okay? One last time, conjugates are when you have the same two terms, 8y and 1, 8y and 1, but they have opposite sign, plus in one of them, minus in the other. Well, let's try another of these. When I see 144x squared minus 49y squared, my brain and your brain will say, well, 144 is the square of 12. So 144x squared is the same thing as 12x squared. Why? Because when I take 12 and I square it, I get 144. When I take x and I square it, I get x squared. Now I see a minus sign. And then when I see 49y squared, my brain would immediately turn this into 7y squared. And your brain does that too now, because when you see 49, you say that's 7 squared, and then y squared is y squared. So this is the difference of two things that are squared. So I can write the factored version by creating two binomials. I put 12x at the start of each one, and then I put 7y at the end of each one, and then I separate them with addition and subtraction, and I'm done. I have just factored the difference of squares. Okay, so there you go. This is the difference of squares pattern. Nobody's going to tell you that this is the difference of squares. You have to recognize it. Nobody's going to tell you this is the difference of squares. You have to be the one that recognizes it so that you can use the pattern and make your life really easy. Okay, now let's go ahead and address a few more of these. We'll do two more. And these two more, maybe they're a little more complicated than the previous ones, right? We're trying to increase complexity as we go. Okay, so let's go ahead and jump into this next one here. I see 48 x to the fourth y squared minus 243 y squared. And maybe there's a GCF. Before I try to apply the difference of squares pattern, I might try to look for a GCF. Why would I do that? Well, because these aren't perfect square values. 48 is not a perfect square. 243, not a perfect square. Those weren't on our lists, okay? So perhaps there's a GCF that we can factor out first. And so I think for a second and I say, what is the GCF of 48 and 243? And you might pick up a calculator and start dividing out 1, 2, divide out 3 out of them, and then continue forward. And you would come to the conclusion that 3 is a GCF of these things. Okay, so if I divide 3 out of 48 and 243, then they come out clean. And I also see that there's a y squared in both of these. So I can factor out a y squared as part of the GCF. We have now found the GCF. It's 3y squared. And the stuff that's remaining, right, when I take this term and divide out that term, is a 16x to the fourth, and then minus an 81. There we go. So I first always look for a GCF, right? We've trained you in previous lessons to always search for the GCF if that's possible. At this point, I notice that this number 16 and this number 81, they are perfect squares. So I can now factor this with the difference of squares pattern. And so I will do that. And first I'll show you that, I turned 16x to the fourth into 4x squared squared. Let me show you why I would want to do that. So 16 is, the perfect square of 4, so 4 squared is 16. And then, well, I've got x to the fourth right here, and I'm going to break it down into x squared squared, right? One of our rules of exponents is the power rule. When I have x squared and I square it, I can multiply the exponents together to make that resulting exponent. So we're kind of using the power rule of exponents backwards. And then I see this minus sign, and then this is easy. 81 is just 9 squared, right? Okay, so I see the difference of two things that are squared. And so I can write my final answer. I'll go ahead and do that. So I've got the 3y squared that I factored out as the GCF. And now I create two binomials. And I put 4x squared at the start of each binomial. And then I put 9 at the end of each binomial. And then I put a plus sign and a minus sign, right? Because they're conjugates. These two binomials are conjugates. They have the same two terms with opposite signs. Great. Now let's look at a very special case. Sometimes this will be hard for students to see, but I want to show it to you. I've got this x squared minus 6x plus 9 minus y squared. And since you've already learned about a perfect square trinomial pattern, you may recognize this, these first three terms are a perfect square trinomial. And in fact, we can factor that into x and 3 with a minus sign, and then square that. Okay, so x squared minus 6x plus 9, that's a perfect square trinomial. We take the, the base of the thing that's squared, right, x, right? X is the base. And then turn 9 into 3 squared, right? And we see 3 is this. And why did I put a minus sign? Because of that. And I squared it. And now I have a minus y squared, right? The remaining stuff that I haven't used yet, minus y squared. And so now I notice that this is the difference of two things that are squared. This is the difference of squares. And so I can use my factoring pattern where I would use, well, the first thing that's squared, x minus 3. So that goes at the beginning. And then I put y, right? The second thing that's squared is y. And then I put a plus between and a minus. And I'm now done. I have factored. Great. So this is, kind of a special scenario where I use the perfect square trinomial pattern to factor it. And then once I factored it, I see the difference of squares pattern, and I factor that. And I have now finished this off. It's x minus 3 plus y times x minus 3 minus y. And here we see the conjugates, right? The plus and the minus between the two things that were being squared. And now we'll move on to our final factoring pattern of the day. And this factoring pattern is called the sum and difference of cubes. All right, it's actually two patterns, the sum of cubes and the difference of cubes patterns. So here they are. So if a and b are real numbers, then if I see one thing that's cubed plus another thing that's cubed, I can factor it into this. So I take that a and that b and add them together. And then I take and create a trinomial, a squared minus a times b plus b squared. Great. Now, what if instead of the sum of two things that are cubed, I have the difference of two things that are cubed, right? A cubed minus b cubed. I can use a factoring pattern, and it's a minus b, right? Whatever those bases a and b are, boom, boom, and multiplied by a squared plus a times b plus b squared. So these are the factoring patterns for the sum and the difference of cubes. Raising something to the third power is called cubing it. Let's go back for a second, because when you use the sum and difference of cubes pattern, you must know your perfect cube values, right? So we're going to see numbers like 1, 8, 27, 64, 125, 216, 343, 512, 729, and 1,000. And we're going to have to turn, if we see 729, we're going to have to turn that into 9 cubed, or 343, we turn it into 7 cubed, etc. So make sure you're very familiar with these values, and when you see them, you'll have to turn them into their number that's cubed. So we think of it backwards in a way. Let's jump into 4 examples to finish off this lesson. So I'll help you see the sum of cubes and the difference of cubes pattern. Now, when I see x cubed plus 64, my brain quickly decides to rewrite it. And so I say, well, that's x cubed plus 4 cubed, right? 64 is 4 times 4 times 4. It's 4 cubed. And so this is the sum of two things that are cubed. So looking back at our factoring pattern, I can write that is x plus 4. Now let's go back right here. So I'm using this sum of cubes pattern, x cubed plus 4 cubed. it equals x plus 4 times x squared. Okay, so the first thing squared minus these two things, x times 4, right? So we're multiplying these two things together. That's x times 4, and we put it right there. That's 4x. We can write that as 4x. And now we add whatever the b value is squared. So in this case, 4, I'm going to square it, and 4 times itself is 16. Okay, so we have now factored the sum of cubes. This is the factored version. And you might ask, well, here's a trinomial. Could we factor that further? And the answer is no, because these trinomials that result are not factorable further. We cannot factor this trinomial. Some trinomials are not factorable, and some are. This one is never factorable. So you never have to try to factor these any further. They can't be factored further. Great, so we just had our kind of first exposure to the sum of cubes. Okay, what if I had, instead of the sum of cubes, I have the difference of cubes, right? I have a minus sign here. So I'm going to, in this case, be using the difference of cubes pattern. So I'll jump in here, and first we want to rewrite these. So, 27, that's the perfect cubed of 3. So I'm going to rewrite this term as 3u in parentheses cubed, right? Because 3 cubed is 27 and u cubed is u cubed. So this is rewritten as this. Now I see the minus sign. And when I see 125, well, that's 5 cubed. So I can say this is 5v cubed, right? Because 5 cubed is 125, v cubed is v cubed. Now that I have rewritten this as this, I notice that it's the difference of cubes, and I jump into the factoring pattern, which is, I'm going to just show you it's here above. We're going to use this factoring pattern. These factoring patterns are on your test formula sheet to refer to, but you have to know how to use them for your success. Well, what I'm going to do is I'm going to take 3u and I'm going to subtract 5v. Okay, and so that's the binomial that results here. That's the a minus b, 3u minus 5v. And now I multiply by a squared. Well, 3u, I'm going to square that, and that gives me 9u squared. Because 3 squared is 9, u squared is u squared. Now we're going to add a times b. So it's 3u times 5v, and 3 times 5 is 15, and then I have the u and the v that are multiplied with it. Next, we're going to take the b value and square it. So 5v, I'm going to square that. So 5 squared is 25, and v squared is v squared. So there I have completed the factoring pattern for the difference of cubes. Okay, well, let's try moving on. Just one sec, I'm going to clean this up a little bit. See if I can get rid of this parenthesis to clean this up so that it's clear. There you go. So what if we run into a case where we see like 6x cubed y plus 48y to the fourth? I would say, well, that's not the sum of two things that are cubed currently, but maybe there's a GCF, because we always want to check for a GCF as we start looking at a certain problem. And so, I would look, what is the GCF of 6 and 48? And the answer is 6, because 48 is a multiple of 6. And then, well, this term doesn't have any x's over here, even though this does. But both the terms have a y in them, so I'm going to factor out a y. So I have found the GCF, it's 6y. And what remains is x cubed plus 8y y cubed. There we go. So if we factor a 6y out of these two terms, we're left with x cubed plus 8y cubed. Now this, the stuff in parentheses, this is the sum of cubes. And I'm going to help you see it even more clearly because I'm going to take this x cubed and I'm going to rewrite it as x in parentheses cubed and then add, well, this 8y cubed, I can turn it into 2y cubed because 2 cubed is 8 and y cubed is y cubed. So you're going to have to break that apart into these pieces. That's when you can see the sum of two things that are cubed really clearly. Okay, so to factor this, first of all, don't forget about the GCF that we factored out, right? We pulled out a GCF at the beginning of this problem. It's still there. And now we can factor the difference of cubes pattern. So I'll set it up, and we take x plus 2y, and we put it right here, right? We just look at the bases, x and 2y, and we're putting addition between them. Now, take the first term and square it. So x, we square it. We write x squared. Now a minus sign. Now we multiply a and b together. These two terms, x and 2y, well, that's 2xy. You see, a little more space here. Now we take the second term, 2y, and we square it. So 2y gets squared, which gives us 2 squared, which is 4, and y squared. There we go. We have factored the sum of cubes. So the starting point was here. We found a GCF. Always factor out a GCF when possible. What remained was the sum of two things that were cubed. What are those two things? X and 2y. We took that x and that 2y and we put it into the sum of cubes factoring pattern, x plus 2y times x squared minus 2xy plus 4y squared. Let's look at a last example here. Okay, so here I see two things that are cubed, right? I see x plus 5 is cubed, and then 64x cubed. So let's clean this up a little bit to see it more clearly. Now, this stuff doesn't clean up at all. It's just what it is, x plus 5 cubed. But I can turn the 64x cubed into 4x cubed because I recognize 64 is a perfect cube of 4. It's a perfect cube of 4. Okay, so 4 when I cube it becomes 64, and x cubed is x cubed. So now I have the difference of two things that are cubed. So I'm going to now factor by writing those two things, which are x plus 5, and then I put a minus sign, right, because this is the difference of cubes, minus 4x. So that's what I get. Now, I multiply that with x plus 5 squared plus x plus 5 times 4x. Right? I'm multiplying those two things together. I'll write it as 4x times x plus 5 because multiplication is commutative. I can write it in any order I want to. And now I add that with, well, 4x squared. I square that second piece, and 4 squared is 16, and x squared is x squared. Great. So we have gotten it to this point, and we'll call that good. We could take it further and clean it up by, like this x plus 5 squared. We could expand it, and we could distribute this 4x in here like that. And we could combine this x and this minus 4x because they're like terms, right? So there are certain things that we could do to expand this, but for the sake of today, we will just leave it like this. All right. Thank you you have now learned 3 factoring patterns in this lesson. Little reminder, you're going to want to be very familiar with these perfect square numbers and these perfect cube numbers like you've seen. And we learned about factoring perfect square trinomials and factoring difference of squares and factoring the sum of cubes and the difference of cubes. All right? So I hope you have a wonderful day. Thank you and take care.